Hello children, do this problem. Welcome back. Okay, wait, I have to solve that problem actually. So you could do the thing I said last lesson, where you find ft and then plug it in and find a. There's a very nice shortcut. I'll try to do it right now. So the way I said last lesson was find the net force on the cart, find the net force on the cylinder, divide the net forces by their masses, and then set those accelerations equal. There's a much simpler way to do it. Treat the whole object as one object. Treat the whole system as one object. We're doing A equals F over M. Well, what's the net force? There is a force upward on the cart called normal force. There's a force of gravity on the cart. They add up to 0. There's a force of tension on the cart. There's a force of tension on the cylinder. They cancel. Due to the third law, the force from the cylinder on the cart equals the force from the cart on the cylinder. So the only force we care about is the force outside the system. Fg, which is it's 2mg. Now we're talking about the system, right? So what's m? It's 7m. A great shortcut for a great problem for a great lesson. Let's watch a video.
A castell is a structure formed of human people. It's a human tower. Castells are a Catalan tradition of over 200 years. Today there are over 80 different colliers or teams spread throughout Catalonia. Every 2 years we have a competition. The 12 best teams will perform at the concours in Tarragona. I'm proud to be a member of the Castellers de Vilafranca. The Castellers de Vilafranca have won the concours for 7 consecutive times. We hope to make it 8 consecutive victories. These are very big structures, very big castles, and they require 300 or 400 people at a time to make these kind of constructions, and they can reach heights of 15 meters. The most important thing when we try to make the castles is obviously the safety of the people involved. We have very small children of the age of 4 or 5 who will climb to the very top of the castle. Everybody is working to make sure that this is the safest possible activity for them. This is very important because occasionally castles will collapse. And it looks spectacular, but it can be very dangerous. It's quite common for people to break a leg, an arm, shoulder injuries. As the castle progresses, the pressure builds. Everybody is trying to find a little bit of oxygen in the bottom of the castle. There have been times when people have fainted or collapsed, but you still have to keep going because you have the collective responsibility that you don't want to let the team down. You hear the final music that you know the castle is completed. You can relax a little bit, but you still have to concentrate because this is the most dangerous part of the castle, because if you relax too much, the structure can collapse very, very quickly. Why am I a Casteller de Vilafranca? This is a very complex question, and I don't really have an answer. You can't explain it. It's impossible to explain. You have to feel it. If you feel it, you understand it.
Wow, what a great video. I like how they like have 4-year-old babies climb the tower and be the highest people. Yeah, of course you want babies on top because they're the lightest. But if that's the case, why not just have babies all the way? Just all babies. How come if you want babies on top because they're the lightest, well, don't you want the tower to be as light as possible? Why not just make the whole tower babies? That makes sense to me. Doesn't that make sense? Yeah, seems fine to me. No, not really. You need non-babies in the middle because everyone in the tower has to hold up the rest of the tower. So either you need really strong babies or you need to not use babies until you get higher up. But hey, here's a question. How strong does the person on the bottom or the second last person need to be? Well, maybe you gotta do some physics. Let's say we have a tower of 5 people and it's just like a single person on each level. And let's say they're all 1,000 newtons. Keep it simple, no babies involved. If we're gonna figure out how much force the 5th person applies on the 4th person, it's actually such a pain. Look at the first person, pulled down by 1,000 Newton force of gravity. That means the second person pushes up with a 1,000 Newton force of gravity. No, that's not what I'm care about. That's true. Yes, that's fine. That means the first person pushes down on the second person with a 1,000 Newton force of gravity. And the second person is also pulled down by gravity. No, the second person is pushed down by a 1,000 Newton normal force and also pulled down by a 1,000 Newton gravitational force. So they required upward 2,000 Newton force. Now look at the third person. If the third person pushes up with 2,000 newtons, they're being pushed down with 2,000 newtons of force from the second person. So for the third person, we got 2,000 newtons downward normal force, and also 1,000 newtons downward gravitational force. So the third person pushes down on the fourth person with 3,000 newtons of force. That means the fourth person experiences 3,000 newton force. That means the fifth person, it ends up being 4,000 newtons. But there was obviously a much simpler way to do this problem. If you're talking about the fifth person and their force on the person above them, just treat all 4 people above them as one object. I'm not saying you should objectify people and treat them as objects. I'm saying from a physics point of view, treat these 4 bodies as one body with a mass of 400, with a weight of 4,000 newtons. That's much more straightforward. Oh, if they require a 4,000 Newton force upward, that's what the fifth person applies, and that's the force downward on the fifth person. So on the fifth person, there's 1,000 newtons downward of normal force. There's 4,000 newtons downward normal force. 1,000 newtons downward gravitational force. And therefore, the normal force on the fifth person must be 5,000 newtons from the ground. So the trick to this is like, where am I? Okay, so we learned Newton's third laws. Newton's third law says for every force, there's an equal opposite force of the same type from the object receiving the force on the object applying the force. Newton's second law, F net equals ma, simple equation, no confusion. Newton's first law, so easy, didn't even mention it. Newton's first law says an object in motion tends to stay in motion, but in physics terms it says when F is 0, A is 0, which is already stated by the second law. F equals ma, well, if F net is 0, A is 0 too. So now we get to complex problems. There's a lot of complex problems that we'll look at tomorrow. And all you do is you take second law and you say, it's true for everything. It's true for the first person, it's true for the second person, it's true for the third person, and it's true for the whole tower of people too. So basically you can choose your system. The system could be one person, two person, three person, it could be one block, two block, three blocks, it could be anything. What example do I want to go over right now? I mean, I already did the example with the cards, so let's just do the blocks. Let's say I have 3 blocks, 1, 2, and 3, on a frictionless table, and I push them all sideways with some force. Well, to start the problem, usually treat all 3 blocks as one system. If you treat them as a system, you can easily find A for the system. I'll call it A. And the mass of the system is obviously the mass of all 3 blocks. Good. Most questions wouldn't ask this. Most questions would say, hey, what's the net force on block 2, or the acceleration of block 2? And this is a lot harder, because if you think about just block 2, and draw the free body diagram, well, you'll have upward normal force, downward gravitational force, which is not bad. Usually they'll add up to 0. I drew too low. Fn upward, Fg downward. Good. What else am I doing? But you're going to have a lot of forces. Force F doesn't act on block 2. On block 2, you have a rightward force from block 1, and also a leftward force from block 3. So, oh man, it's so tough. How are we going to solve this problem? There's so many unknowns. Well, we have a really good head start. If we know all 3 blocks are stuck together, ta-da! They all must have the same acceleration. So, this lesson is mostly practice. You're going to see a lot of practice problems listed, and we're going to look at them tomorrow. But this is the block. This is the force from block 1 on block 2. This is the force from block 3 on block 2. And there's a lot of forces. In this problem, there's a force F, but there's also a lot of other forces. The force from block 1 on block 2, the force from block 2 on block 3, the force from block 2 on block 1, and the force on block 3 this is the force on block 2 from block 3. So this is the force from block 3 on block 2. Yeah, usually the system is force from this on this, but it's not super important as long as it's consistent. So there's 4 unknown forces. This shortcut, it seems really crazy that it would work, that you just do F over all three masses to find all 4 accelerations. But it does work. I feel like I'm going about this a little weird way. This lesson will make more sense tomorrow. So yeah. But why does this work? how can we ignore all four of these forces and just look at the force here on the system and ignore all these four forces? Why can we ignore these four forces when we find A for the system? Tell me now. Wow, great job telling me that these two forces are equal and opposite, and these two forces are also equal and opposite. Due to the third law, the force from block 1 on block 2 and the force from block 2 on block 1 must be equal and opposite and add to 0. Normally this doesn't matter. Remember the stagecoach problem I said? Well, for the horse, no, sorry. I'm just drawing an amazing horse. It's amazing, okay. Yeah. Well, we don't care that the force from the horse on the stagecoach causes an equal opposite force from the stagecoach on the horse. Because if we look at the stagecoach, there is a force from the horse, a horse force. We know that there is also a force on the horse from the stagecoach, but that doesn't matter. When we analyze the stagecoach, we don't look at the force from the stagecoach, only on the stagecoach. The force from the stagecoach on the horse doesn't affect the stagecoach, it affects the horse. So, we can ignore it, and the stagecoach can move. Yeah, great. The stagecoach moves. Because the force from the stagecoach on the horse is on the horse, not the stagecoach. If I lost you there, ask me in class to clarify. Since these forces cancel out, they wouldn't cancel out if we're looking at just block 1. If we look at just block 1, the force from block 2 on block 1 matters. The force from block 1 on block 2 doesn't matter. But we're not looking at just block 1. We're looking at the whole system. So all these forces cancel out, don't matter, add up to 0. If we have a nice system, these are internal forces. And F, well, it's outside the system dotted line box. It's an external force. For Newton's second law, F net equals ma. Only external forces matter. Internal forces don't matter. If there's more than one object that are included in the system, that are included in the mass, like the tension in the half-hour machine, the tension in this string doesn't matter because the force from the cart on the cylinder and the force from the cylinder on the cart will be equal, will be opposite. If we're looking at the whole system, they do cancel. If we're looking at not just the system, they don't cancel. If you look at just the cart, they don't cancel. If you look at just the cylinder, the tension doesn't cancel. But if you look at the whole system, it does cancel. So we only care about the external force. Gravity here. Oh, gravity right here. So it's really weird. We'll do this problem one more time, and then we'll take a quick break. So let me slow down and do the do now a little bit more carefully to not confuse you guys any more than necessary. I think this was 5m, and I think this was 2m. Hopefully that's right. So now the trick, treat them all as one big system. There's 5 forces. Ft, Ft, Fn, FG, FG. Which ones cancel? Which ones don't? Which ones are internal? Which ones aren't? Which one is F net? Okay, Ft and Ft are internal forces, they cancel. Fn and Fg are actually not internal forces. I kind of drew them inside the box, but that's kind of confusing, that's not really correct. They are internal forces, but they do cancel in this case. Unless the cart is going to sink into the table or fly off the table for some weird reason, Fn and Fg will add up to 0. The only force that we care about, F net, is Fg on the cylinder, not the cart. So F net is 2 mg. Now we divide by m. And this is m in the system. So it's 7m, 2 plus 5. Acceleration is 2/7 g. Good job, me. Thanks. Now a question. What is Ft? How do you find the tension force? Think about this. If we treat the whole system as one object, or the whole setup as one system, you can't find Ft. Since the internal force cancels, there's no Ft variable we can't solve for. So, check this out. You can find Ft from the cart or the cylinder. There's 2 ways. We'll get two answers that are the same. We can check our answer twice. So do F equals ma, F net over m, for A equals A, for both objects. I'm going to do it really fast because I already know the answer. On the cart, there's only one Ft. And I'll do it for the cylinder too. For the cylinder, there's 2 forces. The net will be Fg minus Ft. Hopefully you're good so far. Hopefully my large head didn't block all of the physics. And the great thing, we know the acceleration already, because the acceleration for the system is the same as the objects. We got an answer. Ft equals 10 mg over 7, based on the cart. If we are physics scholars, we'll get the same answer over here. What's this Ft? Well, it's the weight of the cylinder, because this is all for the cylinder. And the weight of the cylinder is 2 mg. We had to find a common denominator. 2 mg is 14 over 7. We did it. We're amazing. Physics is easy. We'll see you tomorrow for more practice.